All right, great. Hi, everyone. Welcome to the monthly water webinar. Quick announcement before we begin. Our last webinar of the academic year will be on June 17th, and we'll have Michelle Linfelder-Miles presenting that week. So mark your calendar and join us for that. But today we're delighted to have Helen Dahlke presenting. She's an associate professor in the Department of Land, Air, and Water Resources at UC Davis. Her research focuses on biogeochemical cycling, climate change, and water resources management. And today we'll hear about environmental concerns and water conservation benefits of MAR. So go ahead and take it away, Helen. Thank you for joining us.
Thank you, Ellen, for the introduction. Thank you very much for having me. It's really a great honor to be here. And yeah, it's been a while, I think, since I've updated the program team and the water program team on the research I'm doing. So yeah, as the title suggests, my presentation will focus on agriculture managed aquifer recharge, which we sometimes also call on-farm recharge or groundwater banking, and the benefits it can provide for water supply security, as well as, of course, some of the environmental concerns that we have around flooding farm fields. But before I get started, I would like to acknowledge some of my students and postdocs and collaborators, including Nick Murphy, who just recently finished his PhD, Elad Leventhal and Jonathan Gano, who are two postdocs in my lab, my lab technician Christina, and my two really close collaborators, Toby Eugene and Thomas Harder. Let me see, my computer responding? Yes, it is. All right, so groundwater aquifers, as we know, across the world are really increasingly threatened by overdraft. This is not just a story here in California. It is really an issue in many groundwater basins across the world. And so one of these impacted basins, of course, is the Central Valley, as many of us know, an alluvial aquifer system, which really supports one of the largest agriculture economies that we have in the world. And it has really seen a steady depletion over the last century. We have now accumulated more than 160 million acre feet of overdraft, which is about 1.3 times the volume of Lake Tahoe. And really the majority of this overdraft is happening in the Tulare Lake Basin, which is here located in the southern part of the Central Valley. In California, the legislator actually passed a new groundwater management law, the so-called Sustainable Groundwater Management Act in 2014, which requires now overdrafted groundwater basins to achieve balance in the next 20 or over the next 20 years, and to address certain undesirable results associated with groundwater overdraft, including seawater intrusion along the coast, land subsidence, degraded groundwater quality, and any associated impacts, for example, that we might see on groundwater-dependent ecosystems. So yeah, so we started with sort of a classification of the overdraft situation of the many groundwater subbasins we have in California. And of the 127 subbasins in the Central Valley, 21 have been classified as critically overdrafted. Those are shown here in orange in the map on the right. And most of them, as you can see here, are located within the San Joaquin Tulare Lake Basin. And so for these basins, plans, groundwater sustainability plans have been submitted about 2 years ago. That outline how we are planning, or how they are planning, to address the existing overdraft with a variety of supply and demand solutions. But this graph here that you can see here, which is from a report that the Public Policy Institute of California has put together, most plans plan to address the overdraft with groundwater recharge. So almost 50% of the overdraft is thought to be addressed by groundwater recharge, and only about 20% by demand management. And the plan here particularly is that the recharge water or the water for recharge would mainly come from unclaimed floodwater or storm flow from big rainfall events, which is not already allocated to downstream users and in-stream flow uses that we might have. But water availability, of course, is the big issue. The question is really, do we even have enough water available for addressing all the overdraft that we have? And this is in part because California has a huge year-to-year and within-year variability in precipitation, a little bit illustrated here in this graph on the top, which shows the Sierra Nevada precipitation anomaly for the last 30 years. And so we've, particularly in the last 20 years, entered into a drier regime. And once in a while, we get an extreme precipitation year, such as in 2017, where we saw almost twice the annual precipitation of a so-called normal year. But even intra-annual variability in precipitation seems to be increasing, or is maybe even, impacted more and more by climate change. Historically, January, February, March would be our largest precipitation month. This winter, we saw record precipitation in October, a record snow month in December, and then this month was followed by almost 3 months of no precipitation, resulting again in below average precipitation and very little surface water allocations to downstream users. So what one needs to know about climate in California is, of course, that much of the precipitation we get here in the state depends on these landfalling atmospheric rivers, which are, as some studies show, are expected to increase in intensity, but to decrease in frequency. So it really is going to be a challenge to capture excess water when it becomes available. And here's a nice picture of one of those atmospheric rivers we saw in October of last year. So so what do many water districts do? They are planning to continue to use existing infiltration basins that we have, that we've also actually used for decades already to recharge surplus water. But at this point, most of these facilities really have limited capacity and run full on the days when we have excess water, particularly again during these high intensity storm events. So on-farm recharge really provides potentially a very good alternative to capture lots of water in a fairly short amount of time. And so when we have these high magnitude flows occurring, flood managed aquifer recharge or on-farm recharge might be really a valuable technology to divert flood flows onto either active or fallow farmland or other working lands to recharge the underlying groundwater. It can really provide several benefits for ecosystems and also agricultural communities, such as increased water supply reliability, flood risk reduction, drought preparedness, water quality improvements, and in the long term, climate change adaptation. It really covers a broad range of recharge methods, but in this presentation, I will mainly focus on agriculture managed aquifer recharge, short AGMAR, where we mainly use the agricultural landscape, such as vineyards, orchards, or fallow fields to recharge the underlying groundwater with floodwater. And so adoption of AGMAR among farmers in California is really influenced by several site-specific biophysical factors that can range from crop tolerance to flooding or waterlogged conditions, soil ability to percolate large amounts of water, source water availability, as already mentioned, hydrogeology, and of course, we are reliant on the conveyance system, water infrastructure to deliver water from rivers to fields. For growers who potentially grow perennial crops such as grapes or alfalfa or fruit and nut trees, successful implementation of ECMAR really requires careful estimation of particularly the soil aeration status, since prolonged saturated conditions in the rhizosphere can damage crops if there is extended oxygen deficiency. There's also, of course, concerns about the potential to leach residual nitrate from the root zone or vadose zone into the groundwater, which in many parts of California is already elevated in nitrate. So unless we are really flooding fallow fields, this concern about flooding perennial crops in the winter and that we might be damaging the crop, even though it might be in a dormant state due to limited root respiration or redox conditions, is a valid concern. We have here some data from one of our alfalfa trials. So really, if you look into the literature, we haven't really tested that many crops to see how well they are doing in the case of winter recharge. And most studies to date have really focused on the effect of waterlogged conditions for some of these crops here in heavy soils, but heavy soils are also often not the soils we would be picking for a suitable recharge location. So this table here summarizes some of the studies that we have gathered over, through literature research. And we have actually grouped these studies based sorted the studies, but then actually developed sort of a tolerance rating to waterlogged conditions for these different perennial crops. Ranging between 0 and 4. 0 means no tolerance to standing water. 4 indicative of over 2 weeks of tolerance to standing water. So some of these studies indicate that potentially some of these perennial crops can fare pretty well in waterlogged conditions, such as grapes or pecans, but really more research is needed to really confirm how some of the other perennials are doing in winter dormancy and waterlogged conditions. To bypass some of that research, which would probably take decades, one of my postdocs actually developed a so-called a best or recommended flooding duration estimation tool. This tool estimates the so-called safe water application duration for different soil textures, considering also different crop tolerances and root zone depth that we might have for different crops. And so the figure shown here exemplifies the typical soil oxygen content and soil moisture dynamics that we would observe during a flooding event for recharge. Oxygen is shown here in blue in the top graph. Water content is shown in the black line in the bottom graph. And so the safe water application time is shown as the blue filled area. And it's really well known that as soon as we start flooding a soil, the applied water acts like a barrier, preventing entry of oxygen into the soil. And then root respiration and microbial respiration will slowly consume the remaining oxygen until you reach really suboxic or anoxic conditions, which can inhibit root respiration. So this safe water application duration that we are estimating with a fairly simple model does not only depend on the tolerance of the crop to anoxic conditions, but it can also estimate, or it takes into account how quickly a soil will drain after we stop the water application, and how quickly air will re-enter into the soil, as shown here by the inflection point in the soil oxygen curve. And so just to show you how variable some of these soil textures can be, you can see here this texture pyramid on the right. And so, for example, a sand might drain really quickly within a few hours. So then the water application duration is really more or less determined only by the crop tolerance to how much water they can tolerate until suboxic conditions develop. But a sandy clay, for example, would just to drain that soil so that oxygen can re-enter the profile takes 30 to 40 days. So this is really not a suitable texture for recharge, for example. Yeah, so we are also, or we have explored a little bit more, particularly also the drainage part of when we stop applying water on the field, because there's also interest in knowing when can I re-enter the field with heavy machinery, something that we call trafficability, because, you know, when you have a fairly wet soil, you might have to wait a couple days or weeks even to re-enter a field. And I'll explain a little bit what we did on trafficability in one of the upcoming slides. So right now, this like safe water application duration decision support tool that we have developed only exists at the spreadsheet, but I'm working currently with Toby O'Gene and his postdoc Scott Devine to actually code that into another web tool similarly to the SAGB index that we have developed, so that farmers can use it in the field by just tapping on a location on the soil profile that's predominant in that location, and then enter certain crop parameters, like what kind of crop are they growing and how deep is the root zone, to really estimate what is safe water application time in days, as you can see here on the right side. Of course, some of you might be familiar with SAGB, but I always like to highlight it. This is one of the decision support tools that my colleague Toby O'Gene has developed using Serco soil survey data. This index is providing a rating of soil suitability for groundwater recharge and considers 5 major factors critically that are really critical to sustaining crop health, including, you know, rapid depercolation of applied water, topography, or some chemical limitations. And this decision support tool is available in the form of a web tool. If you just Google SAGB, you will find it. Soils are rated on a scale of 1 to 6, ranging from very poor to excellent. And so excellent soils are shown here in green in this map. You can go to the map setting tab, enter an address, and it's using a Google Maps platform, so you can fairly easily locate your location and find out what SAGB rating a soil has. Yeah, so far this tool has actually worked pretty well for some of our sites. Yeah, just some pictures from some of our field experiments. So moving on to another topic here, as mentioned, trafficability is another concern to growers. So another tool that we're currently working on is, together with Toby O'Gene and Scott Devine, is the so-called time to trafficability after a soil has been thoroughly wetted due to flooding or, you know, heavy precipitation. In general, for those of you unfamiliar with the term trafficability, it describes the capability of a soil to support traffic from farm machinery without creating soil compaction or wheel slippage. And so often if you have compaction, it diminishes soil porosity, which is something we definitely want to avoid. And so the trafficability that we have here estimated is defined actually by the field capacity. So if your soil water content is within 5 or 10% of field capacity, depending on soil texture, there might be a risk of soil compaction if heavy machinery is applied on that soil. So using a hydrous Vedos zone hydrologic model, we simulated the drainage time that these soil textures might take to reach a soil water content that is within 5 or 10% of field capacity. And the two maps you can see here on the slide show the median days to trafficability for the month January and February. You can see here it takes between 10 and 25 days for some of the soils in the Sacramento Valley to dry up sufficiently for heavy machinery to enter. And this is mainly because we have finer textured soils in the Sacramento Valley. Yeah, another big concern is, of course, the leaching of nitrate from farm fields to groundwater. And so it's widely known that in the Central Valley, where we have farmed agricultural land for decades, and we've, of course, repeatedly applied manure or nitrogen fertilizer. So we already know that we have, in certain parts of the Central Valley, we have elevated concentrations of nitrate in groundwater. Those are particularly the areas shown here in red in the left map. And so we're particularly concerned in our research to figure out how much nitrate leaching is actually occurring when we are flooding farm fields, and what is the risk of this nitrate to reach the groundwater, since it really represents a public health risk, particularly if groundwater with elevated nitrate is being ingested as, in the form of drinking water, for example. So to investigate the question of, how this winter flooding for groundwater recharge is impacting nitrate leaching, we've conducted several controlled replicated recharge experiments. You can see here a picture of one of our sites at the Kearney Research and Extension Center near Parlier, where we flooded 2 Thompson seedless grape vineyards in the February of 2020 and 2021. And so in this slide here, you can see some of the nitrate and ammonium concentrations that we observed in the pore water of the root zone of the flooded portions of these 2 vineyards. And the top 2 graphs show that one of the 2 vineyards, which was flooded for 4 weeks. The bottom graph shows the other vineyard, which was only flooded for 2 weeks. And so what we typically see here is that as soon as we start flooding these vineyards, that often contain some residual nitrate in the soil matrix from previous fertilizer applications, about 50 to 90% of that residual nitrate that's stored in the root zone will be leached in the first couple hours today with the water we are applying. As we stop the flooding during the soil drainage phase, and when oxygen re-enters the soil, often the elevated soil moisture from the flooding will stimulate the mineralization of organic nitrogen to ammonium, and then nitrification of ammonium to nitrite and eventually nitrate, which again actually can accumulate in the soil and can become available for leaching in some subsequent recharge event that might be happening. Or it can be available for plant uptake in the following growing season. We do not see much of a sign for denitrification in our soils, because often the leaching happens faster than the time it takes to reach environmental conditions that would favor denitrification. You often need to reach suboxic conditions first in order to have denitrifying bacteria to play a role. And by the time when they become active, often the nitrate has already been mobilized from the root zone. We've also, here, this slide here is showing just like some cumulative graphs of the amount of nitrate we leached in both vineyards. You can see much of it depends also on the initial nitrate concentrations we have in the soil. But again, emphasizing it only takes a couple of days to really leach most or all of the nitrate. In some of our recharge plots, we have completely gone down to 0 concentration of nitrate in the pore water. And so yeah, we also looked into potential effects of winter recharge on greenhouse gas emissions, such as carbon dioxide or nitrous oxide, which you can see plotted on the right, again, for the 2 vineyards that we looked at. The 2-week flooded vineyard is shown in green, the 4-week flooded vineyard in blue. And again, one would actually expect an increase in nitrous oxide during flooding if there would be a lot of denitrification happening. Again, microbial conversion of nitrate to nitrous gases. But we really did not see elevated N2O emissions in the vineyard. The only really peak we saw was later in the season during a fertilization event at the end of April, which was the only fertilization event that the vineyard received in that year. So we've used much of the field data that we've collected in our recharge experiments to build a fairly sophisticated reactive nitrate leaching transport model using the saturated unsaturated flow model HYDROS that is coupled with the USGS geochemical modeling code FREAKSY. This model simulates various nitrogen transformation processes such as mineralization or organic nitrogen to ammonium, nitrification of ammonium to nitrate, using actually conditional kinetic rates that depend on environmental factors such as soil moisture or soil temperature or redox conditions. So using this model actually allowed us to explore really various recharge scenarios and also soil management scenarios for different soil types, so that we could explore different, for example, different flooding frequencies or water application amounts and their impact on nitrate leaching or nitrogen cycling processes. So this helps us to, provide better best management practices for AgMar. Again, we use some field data for this. So in this case, we were actually using some soil chemical and hydrologic data from 2 sites located near Modesto and Dahlke. Those were both almond orchards that we flooded previously under a grant with the California Almond Board. One has to know that Dahlke site was just a pure dune sand, so really the best soil you can get for recharge, with a very high infiltration rate of about 13 inches per hour. The Modesto site was a fine sandy loam, which had a hard pan at about 5 to 6 feet. Both had very different residual soil nitrate concentrations. The sand had a lot, about 78 kilograms per hectare, while the fine sandy loam was about 11 kilograms per hectare. So using this HYDROS model or HP1 model, we were able to simulate now bulk nitrate concentrations of the soil pore water leaving the root zone during recharge events. And so in the plots you see here, you can see the bulk or the pore water nitrate concentration as these colored or filled contour lines in the plots in yellow and blue colors. And then on the x-axis, we see the flooding frequency or how often water was applied for recharge. And on the y-axis, you can see the flooding magnitude, which more or less means how much water in centimeters we applied per flooding event. The black solid and dashed lines highlight the 10 ppm and 5 ppm contaminant levels as a guidance that we have as water quality standard. So yeah, what we can see here is for the sand shown on the left, the sand has really the highest nitrate leaching potential at low flooding magnitude. So if you apply small amounts of water and you have a high residual soil nitrate content, you leach a lot of nitrate. Flooding frequency definitely plays a lesser role for the sand, and this is because we have these high infiltration rates, and we typically maintain a really good oxygen status when we flood sand. It doesn't even go to anoxic conditions, so really denitrification plays a negligible role. But we can see that there is definitely a little bit of a trend of increased mineralization of organic nitrogen to nitrate as we increase the flooding frequency. So if you give the soil more time between water applications, you give microbes more time to create nitrate between flooding events potentially, which can increase the amount of nitrate potentially available for leaching. In the fine sandy loam, again, highest nitrate leaching potential at low flooding magnitudes or low water application amounts and short flooding frequencies. But in contrast to the sand, we see a decrease in nitrate leaching potential as the time interval between flooding events gets longer. And this is because we have a finer textured soil, which can reach in oxy conditions quicker, and it can maintain them for a longer period of time. And as a result, denitrification does play a little bit a larger role and can actually consume some of the nitrate and convert it to nitrous gases. Again, overall, one has to keep in mind, all of these plots will change colors depending on what your residual nitrate concentration is in the soil before you start flooding. And so, yeah, to more or less wrap up and summarize here. So we are in the process of developing several additional decision support tools. So the trafficability tool will be an online or web-based decision support tool. Also the safe water application duration tool will be online soon. I think we're looking at the end of summer for those. We've learned a lot about the nitrogen cycling processes in soils under winter recharge. And they're really quite different to the systems we actually see along the coast of California. So anyone familiar with the Managed Aquifer Recharge research that Andy Fisher's group at UC Santa Cruz does, here in the Central Valley, most of the nitrate that could, be a risk for groundwater contamination is legacy nitrate stored in the soil matrix. Often we do recharge with clean water that comes from snow melt or rainfall. And so the main concern is, how do we prevent that nitrate from leaching quickly out of the profile? Along the coast, they typically recharge flood water that comes from agricultural fields is often elevated in nitrate. So the more water you apply, the more nitrate you are delivering to your system. So they mainly actually rely on denitrification in their systems as a process to remove that nitrate. So two very different systems that need to be managed in different ways, which is quite interesting. And yeah, because we have this, well, first of all, because we have this legacy nitrate in soils, it would actually be nice if we could talk to the Irrigated Lands Regulatory Program. I think their reporting form could benefit from a checkbox that just indicates, is a farmer doing on-farm recharge or not? Because we find that this practice in the winter can definitely leach a lot of nitrate, but it can also produce more nitrate through mineralization, which we didn't necessarily expect under normal winter management. So, oh yeah, this was my highlight here. And with that, I would like to thank the many sponsors we have. I should probably put more logos on here. And the many collaborators we have, particularly growers like Don Cameron, who lets us use his farm fields all the time to do research. So thank you very much.
Thanks, Helen. So yeah, we have time for questions. If anyone would like to chime in and ask Helen questions, also feel free to type your questions in the chat, and Sabik and I can also read them out if you'd like to go that direction. I have a couple questions that I can kick us off with. One, like, you know, kind of relating back to your, actually, if you want to stop sharing, right now we don't see your slides anymore. Yeah, there we go. Now we can
Okay.
see you a bit better. So when people are thinking about like climate change affecting surface water, you know, there are always calls for like more storage if we're losing our snowpack. And obviously that doesn't have to be just reservoirs, but using the groundwater storage. And I'm kind of curious to have a sense of like what potential groundwater storage has to make up some of the losses we might have in the snowpack because of climate change, and sort of, and do we still, like, even if we were to capitalize on the natural reservoir we have in the groundwater by doing a bunch of Agmar, do you think we still need additional reservoir storage?
Well, you know, probably my opinion on this one. My answer, the short one, would be no. But the longer, it always needs a little bit a longer response. So yes, the loss of snowpack is something that will unfold a little bit more in the coming decades as temperatures are rising slowly. But that also means, and we don't have much certainty in actually the climate models on how they're predicting precipitation. So it's still not quite 100% clear whether or not precipitation will go completely into a drier regime. But one thing we are expecting is more intense precipitation events, and this is often the difficulty to manage. So with current reservoirs, they were mainly built for, yes, flood management to some extent, but really more for storage. But if we now have more intense peak flows coming in, we might also have to do more reservoir releases to manage these flood flows in the mountains and maintain that flood pool storage, as we call it, so you know that we are not flooding downstream communities. Groundwater, since we have already pumped more than 160 million acre feet out, has plenty of room to store any excess water. I think surface reservoir capacity is around 42, 43 million acre feet in the state. So current depleted groundwater storage is 4 times our surface reservoir storage. But it also provides other benefits. Reservoirs are still losing water due to evaporation from open lake surfaces. If you put the water underground, you can definitely minimize some of the ET losses. But more water underground also provides many ecosystem benefits that we are not really giving full credit to yet. So most rivers in California were at some point connected to the groundwater aquifer. Many rivers now are disconnected, so meaning the water table is well below several 10 or 100 feet below where the stream bed is now. So reconnecting or refilling groundwater storages could potentially reconnect some of these groundwater systems back to rivers and provide in-stream flows, particularly during the summer dry season, which could provide also, you know, potentially cooler stream water that would benefit the survival of fish. Also, we're running out of room. I don't think there's many rivers left where we can put a reservoir. So yeah, and it's expensive. So building a reservoir is several hundred, if not $1,000 per acre foot compared to recharge, particularly on-farm recharge, which is very cheap or can be pretty cheap. And you're probably more familiar with the numbers than I am.
Yeah, no, that's great. Thanks, Helen. And like the SAGB tool seems really cool for like starting to think about like where should we be doing this. And so I'm curious if you could like, yeah, tell us how it's being used. Like, is it being used in practice to try to like optimize where we do this?
Yeah, I mean, we mainly developed it from the point of view of risk management for farmers. So we're asking them to use farmland that is really used for food production. I mean, the main purpose of farmland is to produce food, not to recharge the groundwater. So now we're asking for a dual service here, food production in the summer and potentially, serving as infiltration basin in the winter. And there has been really a movement in the last 10, 20 years to grow more perennial crops. So, if there wouldn't be any agriculture in California, we would just purely look on soil suitability and then also underlying hydrogeology to see, okay, where could be really good locations where water would go really easy into the subsurface. But we can't necessarily ask growers to change their land use. It's up for discussion, I would say. It would be nice if we could do some planning around those topics as well. But let's say, a farmer has invested into a tree orchard, you don't necessarily can remove it in the next 5 or year or so. So we mainly developed SACB to give some indication, okay, if you have a perennial crop, here is a soil that might move the water fairly quickly through the root zone, or here's a soil that has potentially some flow impeding layers. That could, reduce or actually extend the time it takes for the water to infiltrate in the ground or cause water logging. Some of these soils, by the way, are deep ripped, and this is why SACB has 2 versions, a modified and an unmodified version. Unmodified means we are assuming whatever hard pan or flow impeding layer the soil profile has is still there. But you can remove some of these features through deep ripping, and that would be reflected in the modified SACB index, which sometimes or oftentimes improves infiltration.
Cool, thank you.
Thanks.
Yeah, so there's a question from Safik in the chat.
Yeah. Can you speak to the energy cost of MAR, both moving surface water to a suitable location and also pumping that water? Yeah, so for most of the on-farm recharge that we're doing, we are making use of existing water conveyance systems, and most of these water conveyance systems that rely on gravity flow. So they have been designed and constructed so that water always flows downhill and you wouldn't have to pump water. I'm sure there is exceptions to that rule. And what we find now is in some some locations don't actually have a connection to the surface water system, which we sometimes call those white areas or groundwater pumping only areas. So if folks in that or landowners in that area want to do on-farm recharge, they would have to invest into infrastructure, which is definitely a big cost item. And this is the case again with Don Cameron. He is a groundwater pumper only. He does not really have, association with a surface water district. The only surface water he sees is during extreme wet years when the Kings River is flooding, and then some of that excess water is going into a so-called bypass, and then he takes out water from the bypass. He used to have a 7 CFS cubic feet per second pump. He just invested 12 million to buy or to install a 500 CFS pump, and then built a very extensive canal system on his farm to move that flood water to various recharge fields to infiltrate the water on his farm. There's another question by Michelle. I'm interested in understanding your interest in the checkbox on irrigated lands paperwork on whether a grower is doing more. Understand that more N may be mineralizing, but until the amount of N is better understood, what would be the purpose of the checkbox? I think the purpose is two ways. First of all, if you're doing winter recharge, you're leaching potentially all of the residual nitrate you have in your soil, which can be a risk to the groundwater that's underneath your field. With normal irrigation, particularly with high efficiency irrigation methods, we are now assuming we are not leaching as much nitrate below the root zone or, even to the groundwater table. As soon as you flood fields with lots of water, you, at least based on our field data, you're more or less leaching all of it. Whatever you've accumulated over the last season or last years will be moving towards the groundwater table. So that, in my opinion, is worth knowing, because it can definitely cause a temporary spike in groundwater nitrate concentrations in potentially nearby wells. But again, if we have many dry winters where we have really a huge lack of soil moisture, that lack of moisture really limits microbes to create more nitrate through mineralization. Now, if we basically artificially irrigated those soils in the winter, we promoted conditions that some nitrifying bacteria find really favorable to make a lot of nitrate if there is a lot of organic nitrogen. And in my opinion, that nitrate needs to be measured and considered in your nutrient management plan during the growing season. This is why I think we need a checkbox, if not more soil testing.
Then why wouldn't you just promote more soil testing?
I totally agree with you, but they didn't want that.
Well, my main concern is that the paperwork for the irrigated lands program is a nitrogen budget, and it's not really getting at the end hope is to not have nitrogen leaching to groundwater, but the paperwork itself is not about nitrogen leaching to groundwater. It's about a nitrogen budget for the crop. So,
well, but indirectly they do estimate how much nitrate might be left behind, right? Because you're reporting applied and over the growing season, you report your yield, and from that yield, they are going to estimate how much N uptake might have happened. And the difference between the two is what they might consider is available for leaching to groundwater, right? And that number they want to minimize.
well, yeah, yes, of course. I still don't know about the checkbox though, but
yeah. I mean, I was at a meeting at some point with some folks from the water board and some agricultural commodity, not commodity groups, like some, what are they called? Ag commissioner groups, etc. And I brought this up, just knowing whether or not someone does recharge, in my opinion, does change the whole hydrologic and, nutrient dynamic of a field. So just knowing might be useful to even get a sense for, where do we might see some huge swings in the numbers in the coming years as a result. And yeah, I mean, maybe we can have that as a side discussion at some point, how to better do this.
thanks, Helen.
Any other questions?
Yeah, soil testing would be my number one choice. But then it will get to how often should we be doing this? Because I know now they're asked to do one groundwater sample a year, right? And that groundwater number can change a lot too, also over the course of 1 year. So nothing is really perfect in that matter.
Great. Well, thank you, Helen. It was really awesome to get an update on what you've been up to and learn about your research and everything. Thank you, everyone, for joining today. And yeah, join us back on June 17th for Michelle's talk.
What's it going to be about? Do you have a title, Michelle?
I was just thinking of that. I need to reach out to Ellen and speak. If I gave you a title, I may want to change it. So I'll be in touch.
That's all good, Michelle.